What I want to discuss here is diffraction through a slit. Now, I think you guys are all pretty good with this, but explaining it is not that easy. You probably know that whole business with the slit size and the wavelength was very important, and you know about constructive interference and destructive interference. Constructive interference taking place when you have integer wavelength differences in the travelling distance for the wave. So, and you probably all know the Huygens interpretation of all those little points in the space being sources of the wave. The point is, when you've got very small wavelengths compared to your gap, we've said that you get very little, right? You get very little diffraction, right? So the question is, why over here do we not get the wave when we know that from this point here the wave will travel, from this point here we know the wave will travel? But this is the key, what I just drew there. When you look at this, because of the way this slit is and how big it is compared with the wavelength, look at the path difference. Because this wavelength is on this bit of paper maybe 5 millimeters and the slit length is maybe 15 millimeters, it means that from this side to this side it's quite easy to get 3 wavelength difference. Right? Now that gives plenty of opportunity for the two waves traveling from different sides of the slit to destructively and constructively interfere. So we're going to get a lot of interference over here. Now that interference means that a lot of what's going on, you won't get these smooth waves traveling out like that. It's going to be interference. They're going to be cancelled out. Right? So this one might move out here, right? Or this one starts to move this way. The other one has come along and they start to interfere. Because of the size of the wavelength, the next one comes along quite quickly, and so the path difference that it can go, or the path difference that it travels, can easily be an integer multiple number of path lengths, and we can get that interference cancelling out the waves. So it's interference over here which cancels out the waves on that side. Whereas if we had the same gap, but now we've got wavelengths that are a little bit bigger, well, not that one, but something like that. It's never perfect at sea, you know this. This time, however, so we had a wavelength there, it starts to travel, and the one from this side starts to travel, and after, when this wave gets here, we all know that this one has gone this far, this one has probably gone to about here. Alright, by the time the next one gets there, and then it starts to generate its own. The point being that it's already, this one has already got out to there without being really interfered with, because the amount of distance it could travel by the time this wave got here was quite high. And a wave's never going to interfere with itself, so it's not like this side of the wave can interfere with itself and cancel out that. But this one coming along, okay, he can interfere, right? He comes along, and if he had been a really small wavelength, he can send out his little bits, and we can get that interference. We can get the interference of the little bit from this bit interfering with the bit that came from here on the previous wave, and he can cancel them. So it's a mathematical thing, this interference, but being able to explain why this whole wavelength to gap size is so important is a little bit tricky, and hopefully you got something out of it.